In order to figure out the change in enthalpy of various chemical reactions, we'll be looking at two different methods. It's important before we begin to kind of get a background idea of how the energy of the reactants and the products are connected in terms of the value of delta H, as we have addressed in class, but also how the process of going from the reactants to the products is not important. To review, this reaction, as shown, shows the reactants of higher energy than products. That means that on the product side of the equation, we would put the word energy. This graph shows an exothermic reaction where the value of delta H is negative and energy is given off. The next graph looks at not the beginning and the end, but actually the process of going from the reactants to the products. Well, it turns out that the change in enthalpy, delta H, it doesn't matter whether you go the long way or a shortcut or any other way. The change in enthalpy is always the same, delta H. So for that reason, enthalpy is said to be a state function, which means that where you begin, reactants, and where you end is all that is important, and how you get there is unimportant. That's what a state function means. So we are going to be looking at how we can calculate the change in enthalpy, delta H, for a reaction by two different methods. The standard enthalpy of formation values can be utilized in order to calculate the change in enthalpy of a reaction. So let's start off by defining what standard enthalpy of formation values are. If you open your book to the appendices, you'll see a table that has many values, and one of them is marked delta H of formation. And these will be for both elements and compounds. And if you look at the table, you'll see that the enthalpy of formation of elements is actually 0, and that's an arbitrary setting. It's kind of like when we zero a scale or a balance. That's an arbitrary 0, and then beyond that, whatever we put on the balance has a different mass. Well, the enthalpy of forming an element is set to be 0. And the enthalpy change of forming a mole of a compound, whether it's exothermic or endothermic, well, that depends on the compound being formed. But by definition, it is to form 1 mole of a compound from the elements. If you look at the next slide, you can see that a number of these look like chemical equation forming a compound. But if you look at them and you consider the definition enthalpy of formation to form 1 mole of a compound, you can see that both A and E have to be eliminated because the coefficient in the balanced equation has a coefficient of more than 1 compound being formed. But the other part of the definition that is often ignored is the fact that it's forming a compound from the elements. So if you look at the reactants a little more carefully, you will see that only one reaction has only elements on the reactant side. So again, to review, the enthalpy of formation of an element is set at 0 kilojoules per mole, and the enthalpy of formation of a compound is how much energy is both either required or given off, depending, to form 1 mole of the compound from the element. So in this case, notice that we had to use a coefficient in front of chlorine, which was a fraction, in order to only form 1 mole of the compound. Now, in order to calculate the delta H for a reaction, we have products minus reactants. And then we have this sign. This is called a summation sign, which means you're going to add up the enthalpy of formation of all of the products multiplied by their coefficient in the balanced equation, and then subtract from it the sum of the enthalpy of formation of all of the reactants multiplied by their coefficients. So in the next slide, we'll see an example of this. So using your textbook and using the appendices, you can look up the enthalpy of formation of all of the reactants and all of the products. Be attentive, by the way, to the value based on its state of matter. So here we see, well, CO2 is generally, we can think of carbon dioxide more often as a gas than as any other state of matter, unless, of course, we're talking about dry ice. But in this case, for this problem, notice that for this equation, water that's formed is written as a liquid. So when we look up the enthalpy of formation, we'll want to be attentive to finding the value for liquid water as opposed to gaseous water. This value may not be included in your textbook in the appendices, so that's why this value, the enthalpy of formation of glucose, is included here. So if you're using the equation that was given in the previous slide, sum of the enthalpy of formation of the products minus the sum of the enthalpies of formation of reactants, each multiplied by their coefficients. If you use that example, try to set it up using your appendices and calculate the delta H for this reaction. That would be called the heat of combustion, wouldn't it? Pause the podcast while you figure that out. And so, using the coefficient 6 multiplied by the heat of formation of carbon dioxide plus 6 and the heat of formation of liquid water, that sum, both of those products, minus the enthalpy of formation of glucose, which was given in the problem, times 1, since there's only one glucose, plus 6 oxygens. Oh, well, the enthalpy of formation of an element is 0. That's why that is written as 0. When you do all the math and look at all the positives and negative signs you've got to be attentive to, you will get the enthalpy of formation for this reaction. That means if 1 mole of glucose is burned with 6 moles of oxygen, forming 6 moles of CO2 and 6 moles of liquid water, this much energy is given off. Given off because the value of delta H is negative. The second method of calculating the change in enthalpy for a reaction is a way of algebraically adding up several equations so that the sum of these equations give you the overall reaction. It'd be like adding up a number of polynomials and canceling out like terms. So that's the second method, and this second method actually has a name. It's called Hess's law. So in order to use Hess's law, you're generally given some equations, as you see 3 of them given here, that have the formulas of some of the overall equation, reactants or products. Sometimes they're on the proper side, as is CO2 in this example, both on the product side, but it has the wrong number of coefficients. Well, gosh, if we wanted to form 6 moles of CO2, what would I have to do to this value? If this is the delta H for this reaction, if you form 6 moles of CO2, how will this number change? Hopefully you said, well, it would be 6 times that. So we can modify this equation by multiplying it through by 6. Likewise, we can do the same thing by taking this equation and multiplying it through by 6 again, so that we form 6 moles of water. But when we look at the bottom equation, we can see that the glucose is on the wrong side because we want to add these 3 equations up and get this top equation. So in order to add them up, this has to be on the other side. So what are we going to have to do with this equation? We're going to have to flip it around and make the reactants the products and the products the reactants. notice that in green we have the original equation, but when we turn that equation around, not only have the reactants become the products, but now the sign of the value of delta H is flipped as well. Now, if we want to add these three equations up and end up with our overall equation, which is the combustion of 1 mole of glucose plus 6 moles of oxygen, 6 CO2, and 6 water, then we have to rewrite those other equations and have the coefficients in this be appropriate. So I'm going to multiply the second equation, the carbon plus oxygen equation, by 6, and I'm going to multiply this value by 6. And then the second equation by 6. Making that a 3. So now we have three equations. We're going to add them up together. And when we do that, when we add them all up together, we'll see that there are some things that are common to both sides. And so really, like when you add up an algebraic equation and they're common to both sides, we can cancel out like terms. So if you'll notice, on the product side, there are 3 oxygens here, and there are 3 oxygens here. So I'm going to cancel them out. And you'll notice there's 6 carbons on the reactant side in the second equation, and there's 6 carbons on the reactant side, or excuse me, on the product side in the first equation. Likewise, I see 6 hydrogens and 6 hydrogens canceling out. Is there anything else that cancels out? And the answer is no. But when you add these things up, don't you have 1 glucose plus 6 oxygen, 6 CO2, and 6 waters formed? And the answer is yes. I have the overall equation. And if I add this value up, positive 12, 1,274.5 kilojoules, plus the product of 6 times the 393.5 and 6 times this, you end up with the correct answer, which is the enthalpy of reaction. Coincidentally, it's the same value that we found simply using heats of formation. So again, there's 2 methods. One is using heats of formation and adding up the sum of the products versus the reactants multiplied by their coefficients. And the second method is adding up several equations, flipping them, multiplying them to come up with an overall equation that is equal to what was given in the problem. Hope that helps with how to calculate the enthalpy of chemical change.